Hello, my little triglets. Welcome to Trig Video section 3.5. This is called the rational roots and their graphs. Now, rational, first 5 letters spell ratio, so it's a fraction. So we may have a function, f of x is actually made up of two other functions, p of x and q of x, something like that. Where p of x would be x squared plus 7x plus 9, which is a quadratic. Q of x might be broken into parentheses form, the factored form, something like that. Okay, so it's a big, fat, complicated function, but we break it down into things that we do know. Now you're going to be asked to find the domain of some of these. And remember, that's the x input. In other words, what's legal to put in for x. Now, we all know that 0 cannot be on the denominator. So if we look at all of these, if I put a 0 in for x, 0 times these other two is still 0. So that would be a big no-no. If I put a 2 in here, that would make this middle one 0, and 0 times these other two would still be 0. And if I put a -5 in there, that would also make it 0. So we would say the domain is the reals. Oops. Okay, is the reals. However, x cannot be 0, 2, or -5. So you kind of say what it can't be instead of what it can be. Let's try another example. Let's say I have x squared minus 9 over x minus 3. Look at the denominator. What can x not be? Again, it can be the reals except for x cannot be 3, because if I put a 3 in there, the denominator becomes 0. Now, in the book, you're going to see set builder notation. Okay, it's just kind of a fancy way. You'd say domain dot dot equals, and then a nice bracket, x such that x cannot be 3. So, you know, these two things mean the exact same thing. When you get to college, they like the fancier stuff. They also might put it in interval notation, which would be domain, and then parentheses. So it can be everything but 3. So it can go from -infinity to 3. This means not including 3. And then you say union, that's kind of a capital U. In other words, also it goes from 3 to +infinity. So this is saying these two right here both mean not including. So it's saying from -infinity to 3 but not including 3, and then from 3 to +infinity but not including 3. So it's every number in the whole wide world except for 3. Okay, if the domain is just the reals, you can write it as -infinity to infinity. So those are just some other ways to write things. All right, now I'm going to show you some new notation here also. This is called limit notation. Okay, limit notation has to do with the arrows in a graph. So let's start out with y equals 1 over x. If you were to plug that in, either do a t-chart or go to the graphing button on your calculator, it would show a graph that looked like this and this. Okay, it has two different parts to it. We have 4 arrows going on. I'm going to call this one 1, 2, 3, and 4. Those are your different arrows. Now, limit notation talks about the direction that the arrow is going. It's got 2 directions at each arrow. We've got an up and down direction and a right and left direction at each arrow. Even though number 1 arrow looks like it's only going up, it's technically going to the left and up because it's slanted towards that y-axis. Arrow number 3 looks like it's only going right, but it's technically going down and right at the same time. It's just slightly going down. So we have to accommodate both of those actions here. So let's look at arrow number 1. Now we always start out with limit of f of x. Whoops, back it up. limit of f of x. Now that stands for the y, which stands for the up and down action of that arrow. So if you look at number 1, the up direction goes forever. It never stops. So the limit of f of x is infinity. There is no limit, but we have to give it a limit, so we call it infinity. Now what's happening to the right and left motion? So now we look at the x value. This is the right and left. X approaches this line right here, the y-axis, and x is 0 at the y-axis, so it's headed towards 0 from the right side. So it's coming from the right, headed towards 0. So from the right, we put a little plus after the 0. Okay, so that's pretty fancy looking, but let's try number 2 arrow and see. Let's go back to this color. Okay, so we always start out with the words limit of f of x. That's our y. So what's happening with the y at the number 2 arrow? The y is your up and down, so it's going down, 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 down forever, so we say that's negative infinity. Now what's happening with the x, the sideways action here? X is approaching, it's going that way, it's approaching that y-axis, so it's approaching 0, but this time it's from the left, so we put a minus sign in there. Now this only happens with the up and down, where you have the little plus and minus. This only happens with arrows 1 and 2. We don't have that with arrows 3 and 4. All right, so let's try number 3. Okay, number 3 arrow, the limit of f of x. So what's happening with the y component? The up and down, is it going up? Is it going down? Does it have a stopping point, a border where it can't cross or doesn't cross? Looks like it's headed down toward the x-axis. So that's 0 for the y. So our limit for that one is 0. It's never going to cross that line. That's its limit. And what's happening to the x? How far to the right is it going? Well, it's never going to stop. So as x approaches infinity. Now we don't put plus or minuses with infinity, we just leave it infinity. All right, let's try number 4. Always start out limit of f of x. Again, this is headed up towards this x-axis, which is 0 for the y. And what's x doing? It's going left, 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 left. So that's negative infinity. Okay, so that's limit notation. We're going to do another one in class when you guys get there. So if it's a little confusing, just give it time. Practice will make it much simpler. Okay, the next thing we're going to talk about is the vertical asymptotes. Okay, remember that an asymptote is a boundary that you don't cross. So let's say I have x over x squared minus 9 for my equation. If I break up that denominator, it's a difference of 2 squares, so x plus 3 and minus 3. Right now, x cannot be 3 or negative 3. If you drew this or plotted it on the graphing calculator, you would have a dotted line at 3 and a dotted line at negative 3, and the graph would never cross. So let's say you plug this into the graphing calculator, it would look something like this. And then there'd be a part up here, and there would be a part down here. So it's saying x can be anything along this axis, but it jumps over the 3 and the negative 3, and it starts the graph over. Now, what if I made it, let's try a different graph here, x plus 3 over x squared minus 9. That breaks up into, the bottom is still x plus 3, x minus 3, but the x plus 3's can cancel, so the only thing x cannot be is 3. So this graph is going to look a little different. You're going to have your vertical asymptote at 3, and the graph itself is going to look something like this. Again, we're going to use our graphing calculators to help us out with that. Okay, so similar functions, but the graph comes out completely different. Let's look at the next one here. Let's say x plus 3 over x squared plus 9. Now, because of that plus sign, nothing cancels. Okay, we can't reduce this any farther. So there is no number in here that's going to make that 0, because even if I put a positive, a negative, or 0 in there, it's not going to equal 0. So there's no restrictions. So our domain is the reals. I can put anything I want in there and it'll be legal. So the graph for this one, might look something like that. I'm just guessing here, but that means there's no asymptote. There's no boundary that we can't cross. Okay, sometimes you won't have an asymptote, but you'll have like a hole in the graph. Let's take a look at something like that. Let's say I have x squared minus 4 over x minus 2. The numerator is a difference of 2 squares, so x minus 2, x plus 2. Denominator stays minus. Now before you cancel, what happens here? X cannot be 2. But as I cancel, I get y equals x plus 2 graph. Now back to Algebra 1 days, I'm going to go up to 2, put a dot. My rise over run looks like that. So I have a line. However, when I get to 2 for x, it cannot be 2. So I pay attention and I actually put a hole in the graph at that spot. So it jumps over that. And if you try to graph that on a graphing calculator back here, you can graph it and it'll look like this line. You won't see this hole because it's so tiny. You'd have to zoom in about 20 times to see that hole in the graph. All right, a couple more ideas. Horizontal asymptote. We already did vertical. Vertical has to do with the denominator. Horizontal asymptote is a little different. You have to look at the powers in the rational equation. So if I have y equals ax to the n over bx to the m, you got to check out n and m have to be the highest power in the numerator and the denominator. So here's the deal. If n is less than m, then y equals 0 is the horizontal asymptote. Okay, I'm going to just write HA. Ha! We'll teach that horizontal asymptotal lesson. So if n equals m, if those powers are the same, then y equals a over b, so whatever these numbers are, is your horizontal asymptote. And we'll do examples of these in a minute. Now, if n is greater than m, there is no horizontal asymptote. Okay, it doesn't work. We don't need one. Let's try a couple problems here. Let's say I have 4x over 2x squared plus 1. So look at the powers. I've got a power of 1 and a power of 2. Okay, 1 is less than 2, so I have n. Let's go back up here. N is on the top, m is on the bottom. So I have n is less than m, so that means y equals 0 is your horizontal asymptote. So that's your x-axis. So there'll be a dotted line there, and you cannot cross over that. Let's try 4x squared over 2x squared plus 1. Your highest power on each is 2. So n equals m. That means y equals a over b. So 4 over 2 or 2. So y equals 2 is the horizontal asymptote. So when you draw your sketch, you'd have a dotted line at the 2 there. All right, one more here. 4x to the third over 2x squared plus 1. N is greater than m, so there is no horizontal asymptote. That means there's no boundary. Okay. All right, the last thing I want to tell you, just a reminder, if you're trying to find the x-intercept, remember you put 0 in for y and solve for x. Oops, solve for x. For the y-intercept, you put 0 in for x and solve for y. Okay, we'll try one of those in class, but you've done those before, so I'm not going to spend time right now. All right, people, that was fast and furious. Trig loves you, so you need to love Trig back. And then there'll be Trig love floating around the world, and life will be good. Okay, ta-ta for now.